Hi class, I want to continue our discussion and give you some solutions, do a little bit more problem solving for the chemical kinetics. So I have a question here, which actually you won't find in the PowerPoint, but I just thought to make sure you understand what's going on here. We have 4 moles of ammonia that are reacting with 3 moles of oxygen to give you 2 moles of N2 and 6 water molecules get generated. The question states that the rate of appearance of N2 or rate of formation of N2 is 0.27 moles per liter per second. So if that is true, then what rate is water being formed? And what is the rate of ammonia that would be consumed? So a couple of things here. Hopefully you can realize that this is a balanced equation, and for a balanced equation you can write down that 1 over 4 delta ammonia, the change in concentration of ammonia, divided by delta T with a negative sign, of course, and negative sign is because it's a reactant, is going to be equal to 1 over 3, again with a negative sign, delta oxygen over delta T is going to be equal to 1 over 2 delta nitrogen now over delta T, and this is going to go with a positive sign, which is also equivalent to 1 over 6 delta H2O divided by delta T. So if you really think about it, essentially by saying that the rate of formation of N2, they have given us this part. They have given us the d by dt of N2, and that is equal to 0.27. They have given that part. So the first question asks you what rate is water being formed. So essentially you have to take a look at this part of the segment, and you would say that essentially 1 over 2 delta N2 over delta T times 6 is going to be equal to the speed or the rate at which the water is going to get generated. This value is given to be equal to 0.27. 2 goes with 6 3 times, so 0.27 times 3 is coming out to be 0.81 moles per liter per second should be your final answer for that part. The second half of the question says, what rate is ammonia being consumed? So first of all, realize that it is going to go with a negative sign because it's the consumption of ammonia. So you can safely say negative 1 over 4 delta ammonia divided by delta T is equal to 1 over delta nitrogen over delta T. This part again is equivalent to 0.27 delta ammonia divided by delta T is going to be equal to negative 4 over 2, which will go 2 times, so you're going to end up with an answer of negative 0.54 moles per liter per second. So realize here that the negative sign that you're seeing is basically just for the fact that it's disappearance of your reactant, nothing more than that. I now want to go over a couple questions that are present that are given in the PowerPoint from slide number 43 to 50. So I'm going to take a quick look on that as well. The first question is that you're supposed to express for the reaction 2HI, which is a gas, giving you H2 plus I2, and you're supposed to write down the rate of reaction in terms of H2, the change in concentration in terms of H2, and then in terms of delta HI as well. So for the case of delta H2, you would say that since this is a balanced equation, the rate of the reaction is going to be equal to delta H2 divided by delta T. and in terms of HI, you would say since it's a reactant, it's going to go with a negative sign. And for each mole of hydrogen or iodine that gets formed, essentially 2 moles of HI get used up. So you divide the rate there by 2, because the speed with which HI gets consumed is going to be greater than the speed with which H2 or I2 get formed. Another question is, dinitrogen pentoxide decomposes according to the following reaction, and the reaction that's given to you is 2N2O5, and it's a balanced reaction again, gives you 4NO2 gas plus oxygen gas, and you're supposed to write down an expression for the reaction rate in terms of N2O5, NO2, as well as oxygen. We actually did this in class. You can safely say since 2 moles of nitrogen pentoxide are going to participate in the decomposition reaction, the speed with which that gets used up essentially is going to be faster. So for every 2 moles of N2O5 that get used up, you're going to generate 1 mole of oxygen. And since it's getting used up, I'm going to give it a negative sign, is equal to 1 over 4 delta NO2 divided by delta T, which is equal to delta O2 divided by delta T, based on the same principle as we discussed for the HI example as well. Okay, let's go forward. The next question is, what is the overall order with respect to each reactant and the overall order of the reaction described by the following rate expressions? So the first one is that rate is equal to K1A3. Realize there's only one component, so the order is going to be, with respect to it, is going to be 3, and also the total is going to be 3 as well, because there's only one reactant here. The second one is rate equals K2, A, and B. Notice the power here is 1 each, so it's going to be 1 with respect to A, it's going to be 1 with respect to B, and since 1 plus 1 is 2, the overall order is going to be 2. The third one is rate is equal to K3, A, B square. We would say it's 1 with respect to A, it's 2 with respect to B, and it's 1 plus 2, which is 3 with respect to the total reaction. The next question is rate is equal to K4B. Since the power for B is 1, you say it's 1 with respect to A, and since, with respect to B, and since A does not feature, then that basically means that it's going to be 0 with respect to A. Just the same way in the previous case, if B doesn't feature and it's supposed to be there, then you say that it's going to be just 0 with respect to B. Okay, coming back here, the total in this case is going to come out to be 1 plus 0, which is going to be 1. And the last one is rate is equal to K. That means since no concentration, neither A features nor B features, that means it's going to be 0 with respect to both of those, and so the overall order is going to be 0 as well. All right, let's go forward. The question next is, complete the following table for the reaction, which is first order in both reactants. So you're given that you have A plus B, that gives you products, and then a table is provided to you. Let's just draw the table so that I probably will show you how to do one, and you can, just figure out the missing links yourself, and I'll just give you the fill in the blank so that you have the correct answer. So this is 0.2, this is 0.3, this is 1.5. The second one is 0.029. This guy is 0.78, 0.025. The next one is 0.45, 0.52, and 0.033. Okay, so realize that the question says that it's going to be first order with respect to both A as well as B. That means one can write down a generic rate law expression that rate is going to be equal to K times the concentration of A times concentration of B. Notice the exponential here is 1 with respect to each of the two, the A and the B concentrations. So all you got to do now is plug in the values of A, B, and K so you can determine the value of rate. So I'm going to plug in 1.5 liter per mole per second times 0.2 times 0.3, and when you run the math, I'm getting a value of 0.09 moles per liter per second. 0.09. Likewise, you can use the same rate law expression and plug in the value of B, K, and rate, and hence determine the value of A. So you can again use the same method, use the same rate expression. Rate is given to be 0.025, K is given to be 0.78, A is what I'm seeking, B is 0.029. So solve for A. The value of A comes out to be 1.105. And plugging in the value of A, B, and the rate, you can calculate just the same way as we have been doing. The value of K comes out to be 0.14. All right, let's go forward. The next question is, the decomposition of ammonia on tungsten at 1100 degrees is a zero order reaction. So if it's a zero order reaction, since it's a zero order, that means that if you were to write down the rate law, that's going to be equal to K. The concentration is not going to feature because it's a zero order, so anything to the power of 0 is equal to 1. So your rate law is just rate is equal to K. That's what it is. That's it. The next part is calculate the rate when the concentration of ammonia is 0.08 molar. So since the rate constant is what defines the rate of the reaction, whatever is the value of rate constant that is given is 2.5 times 10 to the negative 4 moles per liter per minute. That is going to be the value of rate as well, because again this is a zero order reaction. And the last question is, at what concentration of ammonia is the rate equal to rate constant? Guess what? At all concentrations of ammonia, rate will be same as the rate constant, and the reason for that is, again, since it's a zero order reaction, it doesn't matter what changes you're going to make. It always is going to be just in direct relationship with the rate constant, and you're going to use that value to determine the rate for that reaction. All right, let's go forward. The question is, in the first order decomposition of acetone at 500 degrees Celsius, it is found that the concentration is 0.0300 molar after 200 minutes and 0.0200 molar after 400 minutes. So you have acetone, CH3COCH3, which is giving you some products. Okay, and we have to calculate the rate constant. We have to calculate the T half. We have to determine the initial concentration. And we are told that this is going to follow the first order decomposition. That means I have a generic formula that natural log of A naught over A is going to be equal to KT. I know that general formula. I also know that T half is the half-life when the concentration is going to be half the initial concentration. And so when you plug in the values, we know from from class that T half can be calculated as 0.693 divided by K. So that means if I'm able to calculate T half, I can determine K or vice versa. And I can use this integrated rate law expression to determine A naught as well, because some data is provided to you. So since you're given, let's take it one step at a time. Since you're given the concentration is 0.0300 after 200 minutes, and it becomes 0.002, I'm sorry, 0.0200 after 400 minutes. And so I'm going to use this integrated rate law and say if the first concentration is my initial concentration and the time period during this is 200 minutes, I can say that natural log of 0.03 divided by 0.02 is going to be equal to K times 200. And when you solve for the K, that will come out to be 2.03 times 10 to the power of negative 3 per minute. Now, this is your value of K. You can simply substitute that value of K into the equation for T half, and that will give you the value of T half. And as I'm substituting that and punching it on my calculator, I get a number 341 per minute, or 341 minute rather. And now you can utilize, now that you have these two numbers, you can simply determine the initial concentration that you started the reaction with. So at T equals 0, what might have happened? So going back to the integrated rate law, the only difference now is going to be that your initial concentration, in fact, is the initial concentration, and the final concentration is 0.03. I'm going to use the value of K that we just determined, and I'm going to use the value of the time, which is 200 minutes that is required for this reaction to take place. And you work that out, I'm getting a number 0.045 molar as the final answer for the third part. Okay, let's take it further. The question is, write the rate expression for each of the following elementary steps. So you're given a reaction K plus HCl that gives you KCl plus H plus. So if you have to write down the rate expression or rate law, you would say rate is equal to K times concentration of K plus times concentration of HCl, and that will be your rate expression. The next one is NO3 plus CO gives you NO2 plus CO2. So again, it's only the reactants that participate in the rate expression. So rate is going to be equal to K times NO3 times CO. Realize in this case, I am actually utilizing the stoichiometry which is in front of each of these. So it's important that we work with a balanced chemical equation. But we are able to utilize the stoichiometry, the molecularity, as the order of this elementary step because this is an elementary step. It's not really a complete overall reaction. The last one is you have 2NO2, which is reacting with 2N, which is reacting to give 2NO plus oxygen gas. And if you were to determine the rate, you're going to say that is going to be dependent only on the concentration of NO2, and we are going to write that as a square. And the whole point, the whole reason for that is because you have a 2 right in front of the NO2. So let's take it further and solve the last question of these additional problems that I wanted to do with you. And the question here is that you have 2H2, and that is reacting with 2NO, and that gives you N2. This is also a gas, and it gives you 2H2O. I mean, just by habit, it's a good idea to just make sure that you have it balanced. So 2 nitrogens, 4 hydrogens, and 2 oxygens. We are set. The question says that the proposed mechanism is, so let's just say what's proposed. Proposed mechanism is that 2 NOs first get converted into N2O2. And that's a fast reaction. Okay, that's a fast reaction. And there's actually a typo. This really should be an equilibrium. N2O2 will react with hydrogen, and you get H2O, and you get N2O. And that's a slow reaction. N2O reacts with hydrogen to give you N2 and H2O. And that too is a fast reaction. Okay? The question is, show that the mechanism is consistent with the rate expression. So two things. The first thing that you should worry about is locate the slowest step, because the slowest step is also going to be your rate determining step. And then you basically say whatever is the is your overall reaction, essentially the rate is going to be equivalent to the rate of the rate determining step. So let's see what the rate expression will look like. In my case, it will look like rate is equal to K times hydrogen. I'm going to put an M on top of that, and an O, I'm going to put an N on top of that. Now we are going to take a look at the rate determining step. So there the rate is going to be equal to K times N2O2 times H2. Realize there are no coefficients, so we are going to just stick to 1. Now N2O2, it gets formed in one step and gets used up in another. That makes it an intermediate. That means the concentration will never be high enough that you can actually carry out a measurement. So what you're going to say here is you'll say that for N2O2, in order to determine the concentration of that, for the forward reaction, let's write down the rate for the forward reaction. Rate forward is equal to Kf NO square of that. Rate backward is going to be equal to KB N2O2, and that's about it, since there's only one more. And at equilibrium, rate of forward becomes equal to rate of the backward reaction. And since it's shown that this is an equilibrium reaction, you can actually say that N2O2, the concentration of that is going to be equal to Kf divided by Kb, and we're multiplying that by NO square of that. So I just actually figured out the concentration of N2O2, which is written in terms of NO, which by the way happens to be one of the reactants. So plugging in essentially this value back into the equation, the rate law expression that was given earlier, you will get rate is going to be equal to K times Kf divided by Kb NO square of that, and you have H2. Realize K is a constant, Kf is a constant, Kb is a constant. So you can consolidate this entire thing into some constant K prime, perhaps, times NO square of that, times H2, and the power is 1. If I compare this to the equation that I had already written, you can see that the left-hand side just states rate is equal to some rate constant K times H2 raised to the power of M. I do have a factor of H2 raised to the power of 1 and NO raised to the power of N. So comparing these two equations, you can say that the value of M, which is the power for hydrogen, is equal to 1 and the value of N is equal to 2. And you would say that this is consistent with the rate expression. You can actually write in that format, and you can actually determine the final orders with respect to both H2 as well as NO. Hopefully this screencast helped you. I'll see you in class.